I'll review the problem statement. We have water at 15 degrees C flowing through a nozzle. The nozzle diameter goes from 0.1 meters, so 0.1 meter right here, to 0.02 meters at the exit. The exit speed here is 25 meters per second, which is a little over 50 miles an hour. This statement says that atmospheric pressure prevails at the exit of the jet, and what that means is that the pressure everywhere across this cross-section is atmospheric, which is 0 gauge. So the pressure there is 0 gauge. The goals are the pressure at section 1, so the pressure across this section, and the force required to hold the nozzle stationary. So force, and we're told to neglect weight. I'll connect this to what I already know. When I see fluid jetting out very fast, I think of a jet engine. And this is going to want to move in this direction or fly just like a jet engine. So I'm going to have to put a force on it like that to hold it stationary. In addition, when I draw my control volume, I've sketched real quick here, fluid outside the control volume is going to be pushing on the fluid inside the control volume. So at this boundary, fluid out here is pushing like that. And I'm going to have to hold on to the nozzle like that to counterbalance this force. Key idea is I'm going to need to put some net force on this nozzle to hold it in place. And I know from experience that this net force usually acts to the left, as I've shown it here. When I see a nozzle, I think of analyzing the problem with the momentum equation. And this equation again just simply says that if you add up all the forces, this is balanced with the rate of momentum out, which is, and you can see some fluid flowing across the control surface there, minus the rate of momentum in, and you can see this term right here. In addition, I also recognize that I've got converging streamlines in here. So I can apply the Bernoulli equation from point 1 to point 2, and I can apply the continuity equation for this control volume from section 1 to section 2. And since I've analyzed a lot of nozzles, I know that most nozzle problems I need to apply all three of those equations: continuity, Bernoulli, and momentum equation. And let's go ahead and get started with the problem documentation. As usual, I sketch my situation diagram. I label the key points that I'm going to use on my control surfaces. I write down the data, and notice again that I'm using SI units, save myself some work. I write down my assumptions, and then when I need it in the solution, I put my fluid properties right here. In the goals, notice that I represent force with a vector. When I use the momentum equation, I'm always remembering that I'm dealing with a vector equation. Since my first goal is the pressure at section 1, I think of the Bernoulli equation because that has pressure in it. And so I sketch my situation. I've got my streamline, identify points 1 and point 2 on the streamline. And let's go ahead and apply the Bernoulli equation. So I write the general equation here and do term-by-term analysis, shown in color here. And the reduced equation is right here. And here's my goal, the pressure at section 1, and I know the density, I know the speed at section 2, and so my new goal becomes the velocity at section 1. So I've illustrated my thinking right here, and I have to ask what equation could I apply that gives me the velocity up here at section 1, and the easiest thing seems to be apply the continuity equation, so V1A1 is equal to V2A2. Here's my control volume. I write the pipe form of the continuity equation. I eliminate density from both sides of the equation. I'm left with this equation, and this equation has my goal in it, V1, which is right there, and V2 should be known. And so I can quickly see that I can find both V1 and P1 by solving the Bernoulli equation and the continuity equation together. To find the second problem goal, which is force to hold the nozzle stationary, I apply the momentum equation. And here's the general equation for a steady flow. And so to visualize the forces, I draw my force diagram, which is here. And so my control volume is sketched in green. And there's a pressure force at section 1. Pressure is always compressive. And this is the force to hold the nozzle stationary. And I neglected the body force, so that's not shown on the force diagram. On the momentum diagram, everywhere fluid crosses a control surface, I draw a vector. So I have fluid crossing here, that's outflow of momentum, and I label it m dot v. So that's m dot v2 corresponding to section 2, m dot v1 corresponding to section 1. To apply the momentum equation, I take the sum of forces, and I can see them off my force diagram. And I'm going to apply the equation in the horizontal direction as shown here. So there's the pressure force to the right and the applied force to the left. So those two terms come right here. Momentum outflow, I can see that on this term, and so that becomes m dot v2. And momentum inflow, this term, I can see that there, and this becomes this term. And I do term-by-term analysis. There's my goal, and the only unknown is the mass flow rate. So my new goal becomes the mass flow rate. I apply the flow rate equation. This involves my goal, and everything on the right-hand side, as you can see, is known. So I've got the problem cracked. I have the flow rate equation and the momentum equation, two equations, and I can solve for the force and the mass flow rate. So now I'm completely done with figuring out the problem. Back over my ideas, and I see I can calculate the velocity at section 1 with the continuity equation, the mass flow rate using the flow rate equation, m dot is equal to rho av, the pressure at section 1 with Bernoulli, and the force to hold the nozzle stationary with the momentum equation. Next, I executed my plan. So here's the continuity equation. I rewrote the equation, put in numbers, and the velocity at section 1 is 1 meter per second. I calculated the mass flow rate by using properties at section 2, and the mass flow rate is given here. I applied the Bernoulli equation to calculate the pressure at section 1, did my calculations, and the pressure at section 1, which is one of the problem goals, is 312 kPa gauge. And it's good practice to always label a pressure with gauge, absolute, differential, some descriptor to tell what pressure you're looking at. The momentum equation calculation is rather lengthy, so I did some intermediate calculations here and then put numbers in. You can kind of work through that, pause the video. And I see that the force is 2.26 kilonewtons, and it's acting to the left. And again, with the momentum equation, you want to be very aware of using vector notation because it is a vector equation. In review, when you analyze a nozzle, nearly always we apply the Bernoulli equation, the continuity equation, and the momentum equation. And when I see a nozzle, I always think to myself, there's going to need to be an applied force to hold this nozzle stationary. I'm going to have to design a support. And the third point on the Bernoulli equation is the pressure at the exit plane here is typically ambient pressure, which is usually 0 gauge, and the pressure up here across this section will be greater than 0 in correspondence with the Bernoulli principle. The last point, the momentum equation is a vector equation, so it's very useful to visualize the vectors, make sure you're writing down vectors, think vectors. This concludes this example. I hope you found this very useful. Thank you very much for listening. I really appreciate it, and you have a good day. Bye-bye.